In this video, we'll explore an important feature of probability models, the moment generating function. Consider a motivating example. Suppose I tell you that I have some random variable x with a mean of 2 and a variance of 4. Further, I have another random variable y that also has a mean of 2 and a variance of 4. Since they have the same mean and variance, does this mean that x and y have to have the same model? Not necessarily. For example, x is exponential with a rate of 0.5, and y is normal with a mean and standard deviation of 2. Though x and y do happen to have the same mean and variance, they definitely do not have the same model. Whereas x is skewed, y is symmetric. Whereas x can only take on positive values beyond 0, y can take on any value in the real line. In general, two random variables can have the same mean and variance but look entirely different. As it turns out, mean and variance are just two of infinitely many features or moments of a random variable. The term moment here has a technical meaning. By definition, the expected value of x to the kth power is what we call the kth moment of x. The kth central moment of x is the expected value of the quantity x minus the expected value of x to the kth power. Finally, the kth standardized moment of x is the expected value of the quantity x minus the expected value of x divided by the standard deviation of x, all to the kth power. Each of these moments, for different values of k, tell us about different features of the random variable x. Consider just a few examples, some of which are already familiar to us. First, consider the kth moment of x. When k equals 1, we call this the first moment. But the first moment is just the expected value of x. E of x equals e of x to the first power. Thus, the first moment of a random variable is what tells us about its center or typical value. Next, consider the kth central moment of x. When k equals 2, we call this the second central moment. But this is just another name for the variance of x. Thus, the second central moment of a random variable is what tells us about its spread. Finally, consider the kth standardized moment of x. When k equals 3, we call this the third standardized moment. This particular moment measures the skew of a random variable. Thus, for symmetric random variables, the skew, or third standardized moment, equals 0. Stepping back, we've learned that the k equals first moment tells us about the center of a random variable. The k equals second central moment tells us about the spread of a random variable. And the k equals third standardized moment tells us about the skew of a random variable. And we can keep going, increasing k. However, as k grows, the meaning of the kth moment becomes more and more obscure. Let's apply these ideas to our example. Recall that our exponential and normal random variables share the same first and second moments, or the same mean and variance. However, they start to diverge in their third moment and beyond. In particular, whereas the normal symmetric random variable y has 0 skew, the exponential random variable x has a positive skew of 2. And since these third moments differ, x and y must have different models. Our example illustrates that moments are important to understanding the behavior of a random variable. However, calculating moments can require tedious and repetitive summation or integration. For example, if x is continuous, to calculate the kth moment of x, we must integrate x to the k times the PDF f of x. The good news is that we don't have to calculate each moment individually. We can use a moment generating function, or MGF. The moment generating function for random variable x is denoted by the capital letter M, with subscript x denoting the variable to which it corresponds. By definition, the MGF evaluated at t is the expected value of e to the tx. So in this exponent, t is the value at which we're evaluating the function m, and x is our random variable. We can obtain this expected value of this function of x by calculating its weighted average. When x is discrete, we sum up the possible outcomes of this function e to the tx, weighted by their corresponding PMFs. When x is continuous, we integrate the possible outcomes of this function, weighted by their corresponding PDFs. Personally speaking, it's not immediately clear from this formula why we'd ever care about a moment-generating function. However, we'll come to rely on two important facts. First, a moment-generating function is a function that generates moments. That is, we can use it to calculate the first moment, second moment, third moment, and so on. Second, more often and exciting, at least to me, just like PDFs and PMFs, we can use moment-generating functions to identify models. For example, when two random variables have the same PDF or PMF, it means that they have the same possible outcomes and that these outcomes have the same relative plausibility. Thus, the two random variables have to share the same model. Similarly, when two random variables have the same moment-generating function, it means that they must share all of the same features, the same center, spread, skew, and so on, including even the same obscure moments. And if they have all of the same features or moments, they must share the same model. In this video, we'll focus on the first of these, using moment-generating functions to calculate moments. For example, the expected value of x, or the first moment, is equal to the first derivative of the moment-generating function evaluated at 0. The expected value of x squared, or the second moment of x, is equal to the second derivative of the moment-generating function evaluated at 0. In general, the expected value of x to the k, or the kth moment of x, is equal to the kth derivative of the MGF evaluated at 0. Thus, calculating the kth moment is a two-step process. First, we want to take the kth derivative of the MGF with respect to t. Then, plug in 0 for t. Let's try out this process using an example. Suppose that x has an exponential model with rate lambda. Thus, the PDF f of x equals lambda times e to the negative lambda x for x greater than 0. We could show the old way that e of x, this integral here, equals 1 over lambda. E of x squared equals 2 over lambda squared. Thus, the variance of x equals ex squared minus the quantity ex squared, which equals 1 over lambda squared. Thus, in our two examples here, an exponential variable with rate 1 has a mean of 1 and a variance of 1. An exponential variable with rate 3 has a mean of 1/3 and a variance of 1/9. For practice, let's calculate these moments using a moment-generating function. In order to do this, we first need to build the moment-generating function. Just as is true for PDFs or PMFs of common models, we could look up existing formulas for the moment-generating function. However, let's build the MGF from scratch for practice. Since x is continuous, we can calculate its MGF using the formula here. We can then plug in the formula for the PDF f of x of the exponential model. As we like to do, since it doesn't depend upon x, let's take out the constant lambda outside the integral. Next, we can combine our two e terms. E to the tx times e to the negative lambda x equals e to the negative lambda minus tx. Notice that I chose to write this exponent here as negative lambda minus t instead of positive t minus lambda. This keeps it in the spirit of an exponential PDF. Now this is intentional. It helps us utilize a fun and common technique for simplifying integrals or sums in probability calculations. And it's one of my favorites in that it avoids actually doing any integration. To this end, notice that the integrand, highlighted here, is the kernel of an exponential variable with rate lambda minus t, right? So we have e to the negative something x, and that something is lambda minus t. But it's just the kernel, right? This PDF is missing a normalizing constant. Notice that the PDF for an exponential with rate lambda has a normalizing constant of lambda. Thus, an exponential with rate lambda minus t needs a normalizing constant of lambda minus t, which is no big deal. Since a normalizing constant is just a constant, we can include the normalizing constant inside the integral and cancel it out with its reciprocal outside the integral. Thus, mathematically, we're just multiplying by 1, so not changing anything. The beauty of this technique is that the integrand is now exactly the PDF of an exponential model with rate lambda minus t. And since the PDF is valid, we know that it integrates to 1. Thus, the moment generating function m of t for an exponential model with rate lambda is lambda divided by lambda minus t. I encourage you to go back through that calculation one more time because each step is important. Now that we have a formula for the exponential MGF, let's use it to calculate some moments. For example, we can calculate the first moment, e of x, by evaluating the first derivative of the MGF at 0. And this is a two-step process. First, we must take the first derivative of m of t with respect to t. Some calculus shows that this first derivative of lambda divided by lambda minus t, the formula that we built previously, that first derivative is lambda divided by lambda minus t squared. As an aside, I'll just say not to worry too much about this particular calculus, so how I got from this step to this step. It's not the main point here. Next, now that we've calculated the first derivative, we can plug in 0 for t. Doing so, we've proved that an exponential random variable with rate lambda has an expected value of lambda divided by lambda minus 0 squared, or just 1 divided by lambda. Similarly, we can calculate this second moment, e of x squared, by evaluating the second derivative of the MGF at 0. In this two-step process, remember that we first must take the second derivative of m of t with respect to t, or the derivative of the first derivative that we calculated on the previous slide. Mainly, recall that that first derivative was lambda divided by lambda minus t squared. Some calculus shows that the derivative of this first derivative, or our second derivative, equals 2 lambda divided by lambda minus t cubed. Again, the calculus isn't the point here, so don't worry too much about it. Finally, plugging in 0 for t, we've proved that the second moment of an exponential random variable with rate lambda equals 2 lambda divided by lambda minus 0 cubed, or just 2 divided by lambda squared. In conclusion, recall 2 important facts about moment-generating functions. First, as we've done in our example, we can use MGFs to calculate moments or features of a random variable. But where moment-generating functions will really shine is in identifying probability models and the connections between different random variables. We'll explore this idea together in class.